This webcast talks about how to do the lab energy stored in a spring. So the first thing is to download the template for this lab from PowerSchool page 6.4. When you open this lab, you'll see that the purpose, what we're trying to do is to find the relationship between the distance that a spring is stretched and the amount of elastic potential energy that's stored in the spring. We're going to use a PhET simulation tool, and you'll see the link to that tool in step 1 of the procedure. So you should go to that tool. You'll see this page when you go to the URL, and go ahead and click the play button. It takes you into the simulator. You'll see that the simulator has 3 parts. The one that we are going to use is on the right hand side. It's called energy. Go ahead and double click that. Okay, and then you want to put checks in all of these boxes for applied force, displacement, equilibrium position, and values. Also, please change the spring constant to 300 newtons per meter. Okay, then you're ready to start getting data for this lab. So I'll go back to the instructions here in the lab template, and we've done everything through step 4. We're now at step 5. We're going to complete this table, and so for each row we will set the displacement equal to the value shown in the table, and then we are going to record the value of the applied force. So the first displacement is 0.01. So I'm going to go to the simulator, and I'm going to choose a value of 0.01. You might have to play a little bit to get it. I may just use the arrows to go up to 0.1. There I go. 0.01 meters. And here in red, I see the applied force, and it is 3 newtons. And so I'm going to record that here in the table. Then I want to change the displacement and make it 0.1 meters. And so I'll do that. Let's see if I went a little too far. Oh, no I haven't. I need to go to 0.1. Okay, now I'm at 0.1 meters, and I see that the applied force is 30 newtons, and so I'll record that. And so you may want to stop this video and go get this table of data. You need to fill the full thing out. Okay, but after you've gotten your data, then we'll start doing the analysis. And the first thing that we want to do is to get a scatter plot. So we're going to use Excel to graph this data. So I need to open a new Excel file, and I'm going to create this table here. So the left-hand column had the displacement, and that was measured in meters. The right-hand column had the applied force, and that was measured in newtons. And I want to put all the values of the displacement, and then I will type in my forces. And so you need to get all of this data typed in here. Now I have mine from a previous here we go. And so I'm just going to type mine in here. There we go. Okay. So we've gotten our data, and now we want to get a scatter plot. So remember, you highlight the cells that have all of your data, not the header, but just the cells that have the numbers. You go to Insert, and we want to do just a simple scatter chart. Okay, and when I look at this, it shows me the shape of the data, and this looks fairly linear, which is nice, but I need to do a good job of labeling this graph. So I'm going to click this green plus sign so that I can get titles on each axis, and then let's put this in. So in this particular graph, we have graphed the applied force versus the displacement on the x-axis, this is our independent variable, is the displacement of the end of the spring. That was measured in meters, and the y-axis has our dependent variable, which was the applied force. How much force did it take to displace the spring that much? Okay. Uh-oh, I misspelled versus. Let me go fix that. Okay, so we have a nice graph here, and we could snip this graph and just paste it in our lab report. And so I'm going to go do that right now. Let's see here. Where is it? There it goes. Okay. And then we'll go on to the next page of our lab report here. It says find the slope of the graph and provide the value of the slope here. This graph is very linear, and so I believe you could just use any 2 points to find this slope. I'm going to use probably the first and the last points. And so I'm going to go calculate that slope. And I get 300 newtons per meter. Okay, then we want to describe the meaning of this slope. And so this slope means that for every additional 1 meter that the end of the spring is displaced, the applied force increases by 300 newtons. The common name given to this slope, notice that its units are in newtons per meter. This is what we call the spring constant. And we use a symbol K to represent this slope. And so our physics equation is going to be the equation of that line of this graph, right? And so we need to be clear on how we're naming the dependent variable and the independent variable. So our independent variable is the displacement. And remember from when we were talking about velocity, we learned that displacement is represented by delta x. The dependent variable is the applied force. And we have been using uppercase F with an A subscript to mean applied force. So our physics equation here says that the applied force equals our slope. Be sure to put the units on the slope times the displacement. Okay. So work is the amount of energy that gets transferred to an object by an external force. In order to transfer energy, the force must cause a displacement of the object. And in this lab, our applied force did cause a displacement because it caused the end of the spring to move further to the right, stretching the spring. Just go look at that. See how the spring has stretched a bit to the right. And I could stretch it even more, right, to exaggerate that. The product of the applied force and the displacement equals the work done. In other words, the work equals the applied force multiplied by the displacement. That's the product when you multiply them. And that equals the amount of energy that gets transferred to the spring. So we're going to paste a copy of our figure 1 in this space below. Let's see. I may have lost it here. So I'm just going to copy it again. And it says that we want to choose a value here that is about halfway toward, in the middle, near the middle of this force versus displacement graph. And so I'm going to choose this point right here. And it asks us to write the coordinates next to that point. And so I'm going to put those points here. So I can tell that the displacement here is 0.4 meters. And if I go look at my table, at 0.4 meters, the force was 120 newtons. Okay? Then it asks me to record this value in table 2. And that's further down here, so let's go down to table 2. Here we go. My first value of displacement is 0.4 meters. Okay? Then it says, shade the area between the force versus displacement graph and the x-axis up to and including the value of that delta x1. This area equals the work that was done to the spring. Okay, so I'm going to, here is 0.4, and this is the line of my graph, this is the x-axis, and I'm going to shade this area between the two of them. And it says to calculate that area. The area is a triangle, right? And so it's going to be 1/2 times the base times the height. And so the base here is 0.4 meters, and the height is 120 newtons. And so when I take that math, 0.5 times 0.4 times 120, I get 24. And the units are newtons times meters, Newton meters. And now I'm going to record the value of this work, this 24 Newton meters, down in table 2. So let's go to table 2, and the work is 24 Newton meters. Okay. So then you're going to do the same thing that I just showed you how to do, but we're going to do it for a value of delta x, which is near the end of the force versus displacement graph. So I'm going to bring another copy of that graph, but this time I want to choose a value that's close to the end. And so I'm going to choose maybe this value right here, and I'll write the coordinates next to it, right? And then I'm going to shade the area between the graph and the x-axis that goes up to and including that point. Okay? And I'm going to record the displacement and that area down in table 2. Okay. So after I've done that, it's going to ask me to fill in the rest of this table. So the pie chart for a system that includes only the spring. Well, in the first column here, the spring is at its equilibrium position. There is no displacement. And so there's no internal energy in the spring. Maybell, stop. I'm sorry about that. No internal energy, and therefore there is no pi. Okay? But when we have stretched the spring a little bit to delta x1, we start getting a little pi of energy. And all of that energy is stored in elastic potential energy. When we have stretched the spring further at delta x2, we have a bigger pi of energy. There's more energy stored in the spring. It's still stored as elastic potential energy. And we can calculate the elastic energy stored in the spring. Here it's going to be 0. But we can calculate it because we know that the elastic potential energy is 1/2 times the spring constant times the displacement squared. So at my point, delta x1, so the spring constant was 300 newtons per meter. The displacement was 0.4 meters, and I square that displacement, and so I get 24 joules. This is joules because it's measuring energy, okay? And I would do that also for the column on the right. So in step 11, it says to compare the values found in step 25 and 26. So basically, we have an equation that says that the elastic potential energy is 1/2 times the K times the displacement squared. And I'm going to do a dimensional analysis on this equation. I know that energy, we've said, is measured in joules. So the unit of that elastic potential energy is joules. On the right-hand side, remember when for dimensional analysis, you ignore any numbers because the numbers do not have a unit associated with them. But K, the spring constant, has a unit of newtons per meter. Displacement has a unit of meter, and I'm squaring displacement. So a joule would have to be equal, one of those meters cancel, to a newton times a meter. And so those two units are equivalent. So, using dimensional analysis, we can demonstrate that a joule is the same as a newton meter. In other words, 1 joule equals 1 newton meter. Okay. Let's go on to the conclusions. The elastic potential energy is energy that's stored as a result of a reversible deformation of an elastic object. So we change the shape by, for example, by stretching the spring, we have deformed it. We've changed its shape. And according to Hooke's law, the force required to compress the spring is proportional to the displacement of the spring. We demonstrated this in figure 1. That's this graph right here, because we can see that the applied force versus displacement is a linear graph. We're showing that to be linear. Anything that's linear is proportional. And so we're going to insert the physics equation right here. We've already written that, so I'll let you copy that down. And we also did answer these two questions up above, but we're just copying them here to our conclusions to be complete. The amount of elastic potential energy stored in the spring, it increases as the spring compression increases. That's why we showed in this table that the pi got bigger, right? As we deformed the spring more, it's storing more energy. And so that the potential energy stored in the spring increases. An external force that stretches or compresses the spring transfers energy by the process of working or work. All of the energy transferred by work is stored as elastic potential energy until the spring is allowed to return to its equilibrium position. Right? At that point, it is not stretched or compressed. It is relaxed at its equilibrium position. And the work done by this force is equal to the change in the elastic potential energy. And so we derived the equation that the elastic potential energy equals 1/2 times the spring constant times the displacement squared. The area under the force versus displacement graph equals the amount of work done to compress the spring, and this work closely matches the amount of elastic potential energy stored in the spring. Then there are a few questions here to apply the equations that we've used in the lab.